Hey guys, I had to break this homework video into two parts because I had to take a break and go see the Justice League movie at the Dollar Theater. So now that that's taken care of and the universe is safe, I wanted to go ahead and finish off this homework. So I am picking up at problem number 25, and you can see I have my comfy Georgia Tech sweatshirt on, and I'm ready to do a little pre-calculus homework. So for number 25, the directions, the function looks a little more complicated, and so I got a little worried that I might not know what to do, but it's really just the same as what we've been doing. We want to find the domain and decide whether it's continuous and see if there's any horizontal and vertical asymptotes. Then we'll take a look at it on a graphing calculator and see whether we're right or not. So what I can tell is that in the denominator the only zeros are imaginary, so we don't have to worry about any vertical asymptotes. And then with horizontal asymptotes we can see that the degrees are the same in the numerator and the denominator, so we will go with 3 over 1 is the equation of the line for the horizontal asymptote. So the domain of the function is going to be all reals. So we'll call that negative infinity to positive infinity. And what else did they ask for? Decide whether it's continuous. Well, if there are, let's see, there's a horizontal asymptote, but as long as there's no vertical asymptotes or holes, I believe it will be continuous. So we'll just write continuous. And now let's go ahead and graph it and see what it looks like. Y equals, and let's clear off our other function. So we'll start with 3x squared plus x minus 5 parenthesis divided by parenthesis x squared plus 1 and graph. So I see a little mark over here, and that means it's thinking, but I can't see my graph. So let's see what the window is. Oh, look at that. Our window is teeny tiny. So we were like less than 1 there. So now let's take a closer look. Alright, so see there is our asymptote. We never get above y equals 3, but then so it looks like we have an inflection point at 0, but if I plug in 0 into my function, I don't get anything undefined. So it looks like it just keeps rolling right along. So we were right. In number 27, we have our function. And let me adjust the camera a little bit. In number 27, our function I can already see is a little bit different, a little more complicated. We've got negative x cubed plus 27. So we want to look at the zeros of the denominator. So if x is 3, negative 3 to the third, which would be negative 27 plus 27 would be 0. So we have x cannot equal negative 3. Wait, not negative 3, positive 3. Cannot equal positive 3, so therefore x equals 3 is our vertical asymptote. And then we want to look at the top and see, can that be factored? So want to see if there's two things that when we multiply them they equal negative 4, when they add equal 3. So that's negative 1 times 4. So we have x minus 1, x plus 4 up on the top. So that's going to make our, no, that's not going to make our horizontal asymptotes. Hold on just a second. So one more thing, if I were to rewrite this denominator as 27 minus x cubed, I want to remember that there is a way to factor a difference of cubes. Okay, so it's kind of funny, but I did just ask Siri. I knew I could look it up in my pre-calc book, but I asked Siri how to factor a difference of cubes. So we have this little, let's see, if I have a cubed minus b cubed, there's a factoring pattern that we've learned several times and then forgotten because it's not frequently used. But here is our factoring pattern for a difference of cubes. So my problem number 27 is getting pretty messy over here. So I'm going to go to the next page and just try to neaten it up for you guys. So I started out with f of x equals x squared plus 3x minus 4 over negative x cubed plus 27, and I'm going to call it 27 minus x cubed. So I'm going to factor both of those. So I've got my x minus 1 and x plus 4 up top, and then on the bottom I'm going to use that factoring two cubes pattern to factor. So the cube root of 27 is 3, and the cube root of x cubed is x. So I'm going to have 3 minus x, and then 3 squared, which is 9, plus ab, which is 3x, plus x squared. So this guy has a 0 of 3. This guy has 2 imaginary roots. Then here we have a 0 of 1 and a 0 of negative 4. So nothing cancels. Oh gosh, there. Sorry about that. Nothing cancels, so that leaves me with no holes or anything. But I'm going to have some asymptotes. So my vertical asymptote is at the bottom, and we already said the vertical asymptote will be x equals 3, because as far as the domain, it's all reals except 3. So negative infinity to 3, oops, that's a parenthesis, and then 3 to infinity. So then we're looking up top for our, those would just be zeros, I guess. If x is 1 or x is negative 4, those would be zeros. That would be where it crosses the axis. And then we want to talk about a horizontal asymptote. And again, as long as I don't have these guys memorized, I want to check it out. We've got an x squared over an x cubed. So that's just like my first scenario here in the notes where y equals 0 is a horizontal asymptote. So we've got our domain, we've got a vertical asymptote. So that means our function is not continuous because it's going to rise with our vertical asymptote. Horizontal asymptote is 0, and now last thing, we are just ready to graph this puppy. So we are going to do x squared plus 3x minus 4 divided by 27 minus x cubed. And let's graph it. Okay, so we can see right here at x equals 3, there's our vertical asymptote, and then our function hugs along the x-axis, or y equals 0. So I believe we had everything correct there. Last one, let's take a look at number 29. And that is table of values. And I chose this problem because I really do want you guys to remember, if you are stuck and you're trying to make a graph of something and you just can't remember the parent function or what it does or how it's supposed to move, you can always choose some numbers on your table of values. So let's determine the domains of both of our functions. So here we have an f, we have that the function is never allowed to equal 4. So it's every number in the universe except for 4. Here in G, the domain is all reals, because that's just a linear function. Then we are asked for any vertical asymptotes and holes. So here we have a vertical asymptote of, and let's see, that would be x equals 4. Here we have no vertical asymptote. For the top, let's see, any holes. Ooh, so x equals 4 may or may not be a vertical asymptote. Let's simplify f of x a little bit. So let's go x plus 4, x minus 4, then x minus 4. So look what happens. Our x minus 4's cancel out. So it looks like instead of being a vertical asymptote, that's just a hole. And here there are no holes, because it's just a line. What else are we being asked for? Is it continuous? No, because it has a hole. And any horizontal and vertical asymptotes. So, well, you know what? That explains to me why these two functions are together, because they end up being the same function. It's just this one has a hole where x equals 4, this one has no holes, this is not continuous, this one's continuous, even though they're the exact same function in the end. The fact that f started out with some more to it, I guess, is what the difference is. So now we're going to complete the table. We have x, f of x, and g of x. And x goes from 1 to 7. So we plug 1 in to f, and we get negative 15 over negative 3, which is positive 5. We plug 1 into g, and we get positive 5. 2, we get 4 squared minus 16 is negative 12 over 2 minus 4, negative 2. So that's 6. And then g of x. So pretty much we're going to get the same thing for each one until we get to 4. And then here we're going to have no solution, and here we're going to have 8. So 3 squared minus 16 is negative 7. Divided by negative 1 is positive 7. 9. Yeah, so the pattern holds for everything all the way across except for at x equals 4. So that is it for our 2-6 homework. Thanks for watching.